Hello everyone, my name is Omar Njai. I am a Senior Technical Specialist at Altair, and today I'm going to present you a brief introduction about our neutral durability platform, which is HyperLife. And through a live demo, I will show you the short steps. Here basically 3 steps that we are going to use to set up a fatigue analysis in HyperLife platform. So first of all, allow me to introduce you to introduce the interface. So HyperLife interface is based on our HyperWorks next generation interface. And here we have in this basic profile different menu under this HyperLife ribbon. So let me bring a model and then try to go through different functionalities of this product. So to open a model, here you can go and then load a model here. So as you can see, HyperLife is a neutral platform, so you can import result from different sources. So OptiStruct, FEM, H3D or OP2 file. So we support also Nastran OP2 file, Abacus, ODB, ANSYS RST, LSDyna, D3 plots, or different other file like H3D coming from Altair product or converted from our HV trans, or even HDF5 file. Okay, so you can load here as you used to do in Hyperview, so the model and the results. So if your result file contains the mesh, then this one can be loaded as both model and result file. So when you hit apply, the model will pops up. So going forward here, I was talking about this load case capability. So you are able to create some derived load cases of type envelope or linear superposition. So typically, if you have different unit loads that you want to scale here and combine with other load cases to build a new derived load case, you can use this. You can rename if you want. So for example, derived LSP, and then this will be available in your model for basic post processing. So for example, I have it here, or I can later on have it available to do fatigue calculation. So as I said, in the fatigue analysis, here we have 3 main steps to set up the fatigue. So the first one is to select a fatigue module. So the fatigue modules is simply the type of analysis that we want to conduct. So here we have high cycle fatigue with the SN option, so stress life option. So low cycle fatigue with EN option, which is the strain life approach. We have the factor of safety, which is the Dang-Van multi-axial criteria. And we have also welder fatigue based on RUP for spot welder fatigue and Volvo method for seam welder fatigue. So when I select a module, So this interface pops up and yeah, prompt me to select the method that I want to use for the analysis. So here I have a stress life approach, and then I can solve it using a uniaxial assumption or a multi-axial method. Then depending on the selection I made here, so I have these different options to input. So basically your result file is solved using a different find element code, so a find element solver. So here you need to tell HyperLife what are the stress units that you have imported. Then you, in the uniaxial, you have to select a stress combination, so which is representative to your uniaxial stress state. Here we propose a different stress combination methods. So for example, here I could simply select sign von Mises, for example. Certainty of survival to take into account the material, fatigue material scatter. And then you have the mean stress correction method to deal with the mean stress effects during cyclic loading. And then you can also select here the layer of interest when you deal with shell elements. By default, we propose the worst layer, and then damage will be calculated on both top and bottom layers, and the worst one will be reported as the damage contour. And we have different loading type available. So the time series here is kind of pseudo static loading, which means you will solve static loading typically with unit loads. And in the fatigue analysis, you will scale this fatigue loading with some time series. So the time history data will be used to scale your fatigue loading. And in this way, of course, the dynamic effects won't be considered. So of course, if you have cases where the loading is or the dynamic effect of the loading is not to be considered, so you can go with this option. In addition to that, we have transient response. So typically, if you have a true dynamic loading in the time domain, then you can solve it using a transient response analysis. Import the transient response to HyperLife, and then use directly the transient stress to solve your fatigue. Same we can do with model superposition. So here it will be also a transient response, but which is directly solved inside HyperLife, which means that you have to import the modal stress in HyperLife along with the model participation factors. So as of today, we support stress coming from H3D or OP2, so modal stress, which is to be combined with model participation factor in punch file. And the second option we have for model superposition is the one which use motion solve results. So we can import a flexible body which contain the model stress along with the AMREF file which contain the model participation factor. So when you do the transient analysis inside motion solve, and then we can combine both sources inside HyperLife to calculate the model superposition to get the modal stress, the transient stress, and from the transient stress we can make fatigue. So another solution that we support is random fatigue. So here for the random fatigue we have two different inputs, so we can solve the random response analysis in OptiStruct or in different other solvers, and then import the model, the frequency frequency response directly to make the random response with the fatigue inside HyperLife, or we can solve the PSD analysis, or the random response analysis, with OptiStruct, import the PSD results, and then make the random fatigue. So we have these two cases supported as of today, and we can make also sine sweep fatigue in HyperLife. So for this demo, let's keep the time series. So second step of the setup is the material mapping. So which mean here we will define some fatigue endurance curve and use this fatigue endurance curve to calculate some damage. So typically here in SN method, we are implementing some SN curve or valeur curve, and this SN curve can be obtained from this native database. So we have this native database available, so MaterialDB, this tab, where you can find some aluminum or titanium alloy. You can find some steels some steels or stainless steel as well. And you can also create your own database by importing, for example, a CSV file, or you can create manually your material here using different options to create the material. So for example, here you can input the stress at 1000 cycle, the fatigue limit, and the number of cycle to fatigue limit, for example, to create this single slope SN curve. Or you have different other options. So for example, this one, where you can use the different Baskin coefficient, like SRI1, so stress at one cycle, the two slopes, and the fatigue limit, along with the number of cycle to transition point. You can also use some empirical formula here to estimate the different Baskin coefficients using those formula. So for example, knowing the UDS of the material and knowing the material type, if it is an aluminum alloy or if it is a steel, you can estimate here the SN curve. So for example, typically here if I change the different quantities, then the SN curve will be updated accordingly. And then I can save those plots. I can rename if I want, of course, and add those plots. For example, I can select certain number of them and then have them under this drop-down menu, right? So what I can do also is to select some part here to calculate fatigue on. An option I have here is typically to select, for example, the part graphically, and then check automatically this option in HyperLife. So if I scroll here, I will see one part checked automatically here, and this is the one I want to evaluate the fatigue performance on. So of course here you can make the fatigue directly selecting some parts and excluding some sets here, or I can switch this option and make the fatigue directly to some sets. So as I explained previously, if you make a stress analysis first and then just isolate some area of your component, you can save time simply using sets instead of full components. So this is also an option which is possible. But for this demo, let me simply choose this component. And last step, third and last step of this setup is the load mapping. So load mapping allows you to associate your load cases solved from your fine element model. And by the way, you can see that all the derived load cases created using this utility will be listed here and can be used also to make fatigue. So this increases the possibilities that you have. So typically, if you solve your unit loads with your fine element solver, you can create all the derived load cases that you want to create the real world load use cases and use them in the fatigue analysis. So here you have different way of implementing your curves. So for example, you can simply make some constant amplitude loading. Constant amplitude mean I will cycle with a constant amplitude. So here, for example, +1, -1. Okay, of course, I can scale those values. So instead of +1, -1, I can make +2, -1, and yeah, you can scale this value as you want. I can make also what we call here a block loading, which is nothing but a sequence of constant amplitude. So typically here I can make 3 different constant amplitude, and each one I can scale the min and max. I can repeat them a certain number of times. So for example, for this one I can I can cycle from +5 to minus some value, -3, for example, and I can repeat this one a certain number of times, and so on and so forth. And this will be my fatigue loading. So a sequence of all this loading. Another possibility is simply to import some time data. So here, for example, I can go there from a measurement or from MBD simulation or from whatever source that you can use to build the load time history. So we can simply have this CSV and import it in our model, which will represent somehow the load history that a certain load case will see. And we can pair them. So we have some automatic way to pair them. So here, for example, if I check automatic, I can simply select as many subcase than load channel, and then I can pair them automatically. So typically here I have my load X, which is paired automatically with the channel X, and so on and so forth. And of course, I could also create some sorry, I could also put this manually. I create the event, drag and drop here any load case. So for example, I can drag and drop this load case, and on top of this load case, I can drag and drop, for example, a channel which is associated to this load case. So as you can see, typically here for one fatigue load case, which we call a fatigue event here, I associate different load cases. So by default, all these load cases will be superimposed. So which means for each time points of the different time histories, all these load cases will be scaled, then superimpose, and I will get one single stress history, which will be used to make the rent flow. Again, we have other options. So for example, if I add another load case, let me bring another load case, for example, under this one, and I could set this one, for example, instead of a superposition, I could build a fatigue load case, which is a sequence of different static load cases. Before to leave this one, we need to select the different events that we want to solve. So for example, if I have a certain number of events and then I want to just evaluate this one, I can select this one. Knowing that if I have several events and I check all of them, so the damage will be accumulated for all the events. So I will create a even-wise damage, and I will sum up all the damage to get my total damage. Of course, this kind of load mapping is something that you will use likely several times on different projects, for example, with different loading. For example, some raw load data that you have to use every time on different models and so on. You can export this setup and import them in what we call a HyperLife load map file. So for example, here I could go there and then let's call this HyperLife load map file. So for example, .xml, and then I can open this file. If I go to my document, I can open this file and it look like this. So typically you can recognize the different block loading that I have created, the constant amplitude file that I have created, the different CSV file that I have imported. Here is one fatigue event I have created. Here is the second one. And here is the fatigue sequence that I will solve. So my fatigue sequence is simply this first event, which is called fatigue event 1. So of course I could change, for example, the number of repetition. I could say repeat this one 100 times, save this one in a file, delete everything. So for example, I could use a new model and then simply go there and import my HyperLife load map file, and everything is imported with the different changes I made on this file. So this is some kind of templatization that you can use if you want to iterate on different model. And in any case, if you have typical loadings that has to be applied several times on your model, you can use this HyperLife load map. Of course, similar option is available using duty cycle file. So which is also an XML file which you can get from different sources, and these can be imported directly in HyperLife to import, for example, your row load data along with your directly mapped with your load cases, your fatigue load cases. So that being said, we have ended the setup using our 3 steps. So selection of our module, material mapping, and load fatigue loading mapping. And lastly, I can go there, review my setup. So which part is selected, which material is assigned, what event I want to evaluate here, and I can simply, of course, I could go there and then select the location. So if I want to analyze on the elemental level, or if I have some resources available in the result file to evaluate on a nodal basis. So typically, if you have the grid point stresses, or if you have the corner data, we can evaluate on the nodes. You can make a safety factor calculation based on the diagram that you have here. So for example, if you use a Goodman mean stress correction method, we can use the Goodman diagram to evaluate here a mean to calculate a safety of factor, for example, based on the Goodman diagram. And then I can hit run to solve the analysis. So once it is done, then I can hit here to review my results. And then here I have the different damage value which are available. And here the stress life, the life value, and even we can also look at the safety factor. So here, of course, I have solved only one event, so I have directly my total damage. Otherwise, I could enable here the event-wise results if I have several load fatigue event, and I would see here the list of the events, and I can scroll and select either of them. In this bottom part, you have the callout and the rain flow matrix. So under the callout, you can go there and then select different elements and then get the counting, the results on this element. So here I have the element ID, the damage of this element, the life, and the safety factor if I have requested the calculation of safety factor. And here, of course, we have all these options available for the number of cycle versus here the rain flow. I have mean stress versus stress amplitude versus number of cycle for this element. And I have the same for the damage matrix. And this one can be exported to a, so here basically in my document you have a fatigue. Let me bring it here. You have here the run history, and this is the one I have run just before. And then you can open this one and see the rain flow counting typically. So for example, for this stress amplitude, I have a corresponding mean stress, which is high mean stress. And this stress is corrected to take into account the effect of this mean stress using the Goodman method to ends up with this value. And this value is used to calculate my my damage. And we sum up all the damage through this event. and then to end up with a total damage. And this is pretty much all I wanted to show on this live demo. Of course, the same process applies on the different methods, be it SN, EN, or safety of factor. We have exactly these 3 steps to set up the analysis. So if you have any question, please you can ask them now.